Okay, so while that's buffering there, we'll be almost ready to go. Okay, so before we start, I wanted to mention something here. I don't know if you're familiar with this or if you've noticed that this is hidden in there. Oh, whoops, I'm on the wrong button. Give me a second. So Zoom can see it. Now, hopefully you can see it out here. Again, we're looking right here. Extra office hours. So I know during COVID, everybody kind of got out of the habit of working in person together, right? You tried to collaborate over Discord, but it's not the same as having somebody right next to you and working. And to that end, I've got some extra office hours. These are listed here. There's a bunch of words here if you want to read it. This is on Canvas. Just look for the extra office hours announcement. But notice some of them start tomorrow. These are in the Mesa Center. And notice this little note. You can receive 5% extra credit on one of your midterms for showing up to one of these 4 office hours with me, asking me a question in the Mesa Center. Okay? My reason for doing this is I want to encourage you to take advantage of that resource. And you know how it is. We've gotten out of the habit of realizing it's there, or maybe it's been on Zoom and Zoom sucks, or Discord sucks for you, right? So in order to encourage you to have some in-person interactions, there's a couple of times there. So something you might do is if you're trying to work on your presentation, hey, come in and ask me a question about it, or say, here's my rough draft, or what do you think I should do? Or if you're doing a homework question, all right? So you can only get extra credit once. That's the most common question. So you cannot just come in and ask me, whatever, 20, 60 questions and try and get 100% that way. Sorry, that's ridiculous. All right, there'll be some other students there. But hopefully you learn from this experience that, oh, sometimes working in person is actually nice. I mean, I know COVID's got risks and everybody has different risk tolerances, but I just can't recommend that enough. We've fallen out of that habit, and we think this is one of the many reasons students are sucking at class right now. All right. You know where it is? Do it. Swing by. You got all those times. All right. Next up, I want to talk about, well, let me do this. Let me move this just a little bit. All right. So there's a couple of things that we've been seeing. We've handled word problems with constant acceleration. What about non-constant acceleration? What methods might we have for handling non-constant acceleration? One is calculus. And in particular, a technique we're going to use called separation of variables. More on that in the last half of class. 2, something that we can do is we can split problems into multiple stages. Now, the reason I've got a simulation here, and then we can actually look at a real life experiment and they're related. Let me just go down into here. All right. So hopefully, oh wait, I'm not screen sharing. Let me get that. Hold on. And let me do this. Actually, I know it's a little bit small here, but the reason is I'm going to try and show, well, let's make this big for a second. All right. Looks like we're kind of missing the left edge of there for some reason. That's kind of weird. There we go. All right. So I don't know if you can see these numbers at all, but on the screen in red, there's an object that's going to have an acceleration, but no initial velocity. So that's right here. Notice there's no initial velocity, and it's got some initial acceleration. There's another object in blue that's got no initial acceleration, but it does have an initial velocity. So in this case, we can run this thing and see what happens. When I run it, oops. the object that has to accelerate falls behind, then speeds up, and eventually catches up. Okay? When we look at this from another standpoint, you could, in theory, plot this information. Right? Whoops. And I hope you're starting to see the value of maybe some of this coding, right? This is a classic problem done in every physics class, and we can see what it looks like, and we can try and understand these plots today. All right? But now, in this case, we're looking at this as the blue object was like one stage, and the red object was like another stage. So in this particular problem, the two stages are for two different objects. But we can also do a problem where the two stages are for the same objects. For example, an object accelerates for a while and then goes at constant velocity for a while. So what we want to do today in the first half of class is get good at handling word problems, some of the words that show up, and how you can split these problems up so that we can understand them and maybe code them in theory. Then we'll go back and do some of the calculus here. All right, so this is kind of our goal for today. All right, so we'll come back to that. All right, let me do this now. And I can show you that code at your heart's content later at the end of class. Let me get some lights on and this up here. So why don't you open up, we're going to do problem 2.6 on page 26, I think, is our first problem, okay? I'll give you some tips on how to address it. Point 6, page 26. Point 6, page 26. Thanks, Alan. You're the man. And I think we can hear you on Zoom if you speak up as well. So feel free to get involved. Okay. 2.6, page 26. Imagine there's a deer standing here on the street. Very common in Illinois, where I grew up. Maybe this deer's got some crazy antlers. And then there's a car here. Notice this is a giant radioactive deer that was twice the size of my vehicle, but whatever. Okay. Now, when I'm reading this problem, what was it? 2.6, page 26. Let's take a look. The first step is to draw it. So that's what I'm doing in my mind. I apologize. I should have asked you that. Okay. The first line says, the driver is driving along at constant speed, V. So I label that in my picture. That's a given, right? You could even write the word givens here. Actually, we're going to need a little space there. You could literally write the givens here. V was a given. Then what? What else are we told? Distance D away. We're told this distance here is distance D. Okay. So D is another given. We're told driver takes time T subscript R to react, then slows at constant rate. This is a dense sentence. Okay, but we do know that TR, we're assuming T subscript R is another given, right? So notice the variables that are stated in the problem statement, unless otherwise specified, we assume those are known quantities. So sometimes people will write knowns here as well, right? think that's even what we said last time. So we know those things in theory. Okay, and then what else are we told? Want minimum rate of slowing so car stops before hitting deer. Want minimum rate of slowing so car doesn't impact deer. Maybe it was said slightly differently, but something like that. Okay. In this problem, I don't know, what does this green sentence here mean? The driver takes time to react and slows at constant rate. What does that tell you? Or what information does that mean, or physically describe what that means, I guess, or how might that relate to some variables or equations or anything? Like this, slows at constant rate. Yeah, slows at constant rate. Sorry if my question was too vague. And I'm going to say it this way. Constant acceleration, opposite sign of v, which in this case is exactly like you said, negative. Nice. Does that make sense? Slowing has to do with accelerating, right? Not velocity. So that's the key word that makes you think, oh, slowing at constant rate is supposed to be constant acceleration. So far, so good? What is this question asking us to find? What are we trying to find?
When velocity is 0.
We're not trying to find when. When makes me think of time.
Oh, sorry.
Right? No, but no, that might relate to what we're trying to find. And I think, yeah, that would be something we could determine, but that's not what we're looking for. What do we want? We want the acceleration. So this is saying determine A. Okay, so far so good. Now in this case, this to me is a classic two-stage problem. There's time while the driver's reacting, and then time while the driver is slowing. So oftentimes what I would do, put a little dotted line here and say, what is true about the acceleration while the driver is reacting?
Positive.
It's constant, but what constant?
So you can get a constant.
That's while it's slowing. So here, there we expect the acceleration should be negative. While you're reacting, what's the acceleration?
To 0.
0. Think about this carefully. And this is a subtlety that I want to point out in the problem statement. It says the driver drives with constant speed v. That speed should continue to be constant until the reaction is done. Agreed? You're going to, so that's kind of somewhere in here. And already I can see something that's going to confuse me if I was writing this on my paper. I see that there's two different accelerations. Shocking. Let's label this one with a 1 for stage 1, the first half of the problem, and this one with a stage 2. And this is basically the trick that you want to get used to doing. You take a problem that was too complicated for us to solve because it wasn't constant acceleration, right? It was 0 and then it was something. You split it into two problems, one with constant acceleration of 0, the other with constant acceleration of something that we're looking for. Got it? And I know you could try to do this all in your head, but from experience, history tells me it's better to get it on a piece of paper and let the paper help me figure all this crap out. All right. Well, maybe I'll say it like this. Now, wait a minute. How do I know that it's actually going to travel the full distance D? If I'm driving and I react to a deer and I start hitting the brakes, it's very likely I'm going to stop well before the deer. Agreed? In fact, that would be advisable. I don't want to get close to this deer. Right? I don't want to cut it to the, like, literally be brushing against its fur. So what lets me know in this problem we're actually going to travel the full distance D, or are we not going to travel the full distance D? Minimum. Outstanding. When we see this minimum here, right, that's the slowest possible rate of slowing. If we were any slower, we would hit the deer. So that word minimum here, in this case, doesn't mean do calculus. Right? It doesn't mean take the derivative, set it equal to 0, solve for a critical point, plug it in and find the value. That's not what we're doing. It's saying, look, if you were any slower on the brakes, you would hit the deer. So that means you must be taking the full distance that you've got available to you. Is that okay with that? All right, so now what we would do is we might make 2 separate lists. Just like before. If you're curious, I don't care about the order of the subscripts. In particular, right, if you wrote V initial for object 2, that's the same thing as V2 initial, in my opinion. So even I will sometimes flip these back and forth. Since we're doing an X problem, you might actually stick on the subscript X here, but I'm just being a little bit lazy today. So the idea is you could color code this and use subscripts, right? And the idea is stage 1 would be the first part of the problem. Stage 2 would be the second part. Oh, crap. I screwed up my color code, didn't I? I'm going to fix that because it's going to annoy me. Okay. Stage 1, I started drawing in blue there. Do you see that? So I
changed the subscript, right?
Yeah, there we go. But then it's going to annoy me because it's whatever. Now I've got 2 coming before 1, but whatever. Sorry about that. Paying attention. So wait, blue is number 1 in my pictures. Sorry about that. And then red is number 2. Obviously, you would want to put 1 before 2, but sorry about that. I'm in a hurry. Okay. Let's take a look here. Let's first fill in anything that we know. Okay. For example, let's start with stage 1. Do we know anything about stage 1 that we can fill in the chart?
A.
A is
0.
0. How about T1?
It's TR.
It's TR. So now I can see that this particular time is going to be TR, but not this time. Do you agree?
Yes.
All right, let's keep going. Do I know V1 initial and V1 final in this problem?
It's constant, so they're the same.
That's right. That's right. Do I know delta X1?
I don't think so.
What does delta X1 mean? Is it position? It's displacement. In this particular problem, why is it okay to use the words distance and displacement interchangeably? For this problem, we can do that. Why? It doesn't reverse directions, right? So in this type of problem, hey, distance displacement is going to be the same, right? It's all to the right. It's all positive. There's no flipping. There's no going backwards. So we're good. But I don't know it. But I could say distance and displacement interchangeably today for this problem. How about delta X2? Do we know that? What's that? X1 minus what?
I think what you're saying is x1 minus x2.
Okay,
There you
I tell you what, let me just say this. Do you know delta x2 immediately? Do you know a value for it? That's this change in distance. Do we know the change in distance right now?
go.
No. And you're saying maybe you could get it from some subtraction. We'll talk about that in a minute, but we don't know this either. That's not going to help that much. So I think the point is, right now we don't know that. Absolutely, we're going to incorporate that fact that you just said in a minute. What's V2 initial? I heard somebody say V. How do you know it's V? Kind of what's the thought process in your brain? Yeah, and I would like to say it this way. The final for stage 1 becomes the initial for stage 2, because that's the point they have in common. Okay, so that's going to be V, outstanding. What's the final velocity of object 2?
It should be 0, right?
What?
That's when we're stopping.
We're trying not to hit that deer, so we should stop. Outstanding. A2, do we know what that is?
Not precisely. That's aside from it being less than 0.
Yes, we don't know it, and in fact, that's WTF. What to find, agreed? That's what we're looking for. Good to keep that in our brains. Do I know how long it's going to take over here? No. Okay. Now, with this type of problem, you were saying something extra. And that was a smart thing to do. There's oftentimes in these two-stage problems, there's some sort of connection. Sometimes we'll call that a constraint. You know about Lagrange multipliers, good for you. Okay. Now, the constraint, I think you were telling me something about the x's and how they're related, right? How do the x's, or the delta x's, I should say, relate? They add up to d, right?
Yes.
So don't overthink it. We know change 1 in position plus change 2 should equal d. Do I need to worry about any plus minus signs on this equation? Because these technically are displacements. For this particular problem, do I need to worry about it? No, because everything's positive. But if you were worried, you might stick absolute values on it. Okay, so far so good. Similarly, even though we don't have this, we could probably write down an equation for total time, right? Do you agree a similar equation would be valid for the times in this case? Not that we need that, but I'm just going to write it down. So here's the deal. When you're doing physics problems with multiple stages, this is the key. You need to be able to read the problem, draw a picture, list all your knowns, being careful about which things are 0 and which things are equal to the final and the initial, etc. And then you need this extra step of coming up with the constraint equations or the connection equations, right? This is the extra step that's different from a normal problem. After we do all this, generally speaking, what do we normally do as the next step? We've got a picture, we've got some knowns, we've got some unknowns. What's that? Equations. So in this case, we got to be careful. We're going to need 2 sets of equations. So I'm going to show you like this. What I would do, now unfortunately I put one over here. So I'm going to do I'm calling this stage 2. Because I put the stage 2 on the left on that side of the board, I'm going to do it again here. I apologize. We're reacting. Okay. So then we could do this. Now you don't have to do what I do, but I recommend it. Wait, this is stage 2, isn't it? Correct. And again, I'm very sorry I put 2 on the left. When you're an inexperienced student, just writing the equations on your paper can help you gain experience. If you're not in the habit of writing these out, get in that habit now. I'm going to do it for both of them. And you can see that it's annoying, but a lot of times you'll be faster at getting the work done. Whoops, this is one. You'll be faster at doing the work if it's on your paper. I know it may not seem like that. It seems like a lot of writing, but usually students are terrible at like trying to think it through in their head. Whereas if it's on paper, you can sometimes do this trick I'm about to show you and at least get some headway. And sometimes that's all you need to get started on a problem. Once you get started, the problems can oftentimes work themselves out. Okay. We've got a bunch of equations. Do you remember what I recommended plugging in before you plug in any of the other values? Plug in the zeros. So in stage 2, what is equal to 0?
Velocity.
Which velocity? Final? Okay, so in stage 2, this is going to go to 0. This is going to go to 0. And I think that's it. Agreed? Stage 1, this is going to go to 0, so it's going to drop out because A was 0. That's also 0. Look at this. This is tremendously less intimidating already. This is just distance equals rate times time, effectively. All right. So now we can do this next step. Let's just put a check next to everything that we know or don't know. Do I know delta x1? Yes or no?
No.
V1 initial.
Yes.
Time. Oh, wait. This is time 1, isn't it? And this one, I accidentally erased a 2 here or forgot to write it. That's a time 2. Sorry about that. Okay, time 1. Do we know it?
Yes. Yes.
Oh, crap. Are we going to be able to figure out delta x1?
Yes.
And then we could use that constraint equation you were talking about. So yes, we could use it. Down here, does this help much?
No.
How about this one?
No.
No, basically, we already know this. Anytime A equals 0, we already know this, right? So oftentimes when A equals 0, I won't even write these equations down. Less work. When A equals 0, this is the only meaningful equation. So far, so good? Now let's go over to here. X2 is unknown. A2 is unknown. T2, unknown. V2 initial is known. T2. That seems like a bad place to start. Do you agree? And that's what we get out of this. You're like, huh, it sure seems like it'd be better to start over here. How about here? Do we know V2 initial? Yes. No. No, not the best. Yes. No.
No.
No. So here we see, huh, this is not looking too good. We see that starting in stage 2 would probably be a bad idea. I'm going to get our constraint equation over here again. Just so they're all on one board. The constraint equation said D was equal to delta x1 plus delta x2. And when we see this all on the board, let's do this one as well. I know D, that was a given. Now take a look. Do you agree in theory we should be able to figure out x1?
Yes.
Agreed? And this is unknown. So in theory, what we could do is use this equation right in here, and then we would know x2. Where would you go after that? Which of these equations might you grab after that? The third one. And so the idea is by writing the equations and just checking what you know and don't know, this gives us a strategy to solve the problem instead of just randomly trying to solve crap. Right? Is everybody good with that? Okay, let's try it out. In this case, do you agree delta x1 is going to equal v t subscript r? Do you agree that's what it turns out to be? What is delta x2 going to give us? If I rearrange this, it's going to equal what? D minus that crap. You agree?
Yeah.
Take a second, make sure I didn't flip a sign or something. I want to do it again. Let's see. So it should be D minus x1, delta x1. D minus that. Okay, I'm feeling good on that. Everybody good there? Now let's take it and shove it into here. Okay, so that's 0 equals V2 initial was V squared. And then this would be some big ugly mess. So far, so good. Now, when I do this one, I want you to watch out for something. I'm going to move this v squared to the other side. So I need to subtract v squared from each side, and I get this. This is what I want you to watch out for right here. Negative v squared is not negative v squared. This is what I mean by that. Negative v squared means negative of v squared, but it's not negative v squared. Not true. Do you know what I'm saying?
Yes.
And just check it, right? Think about this. No matter what number you plug in here for v initial, when you square it, it should be positive. When you move that to the other side, you better get a negative number. So we need a negative number over here. Furthermore, think. We expect this acceleration should turn out to be a negative number. This is actually good. We want that minus sign. This is not canceled by that squared. Enough on that? Just order of operations. PEMDAS, right? This is multiplied by -1. We do that after the exponent. All right. Working this all around, what do we get for A2? I think we're going to get
Squared over 2v squared divided by 2 times.
2 times this crap. Yeah. That's still showing up on Zoom, Alan?
Yeah.
Okay, sweet. Thanks, man. All right. What are some things? And notice this mine. I'm going to make that minus sign pop. I'm going to make it a different color so it really stands out. We do not want to lose that minus sign. What are the things we could do? Well, one thing we could check is, does this have the right sign? We expected for this problem, the acceleration should be negative. This is positive. This down here had better be positive. So we have negative of a positive number. The sign is good. What is another thing we could check?
Units. The units.
Units. What are the units on top?
Meters per second squared. Or second.
Yeah, meters squared over second squared, or meters per second quantity squared, right? What are the units of 2?
Meters minus.
Unitless. What is a D?
Meters.
V?
Meters per second.
T? What are meters minus meters?
Meters.
Meters. Think about it. If I take 16 apples minus 5 apples, I have 11 apples. The units don't disappear when you do a subtraction. So this is good. That's meters squared per second squared times 1 over meters. Is that the right units for A?
Yes.
there's another way we could check this. Let's say you were drunk. What should happen to your reaction time? Slows down. If you are drunk, your TR goes up, right? If your TR goes up, what happens to the minimum required braking acceleration? If TR becomes a slightly bigger number, what happens to the denominator?
Get smaller.
Smaller. What happens to the acceleration required? Gets bigger. So if you're drunk and you take longer to react, you got to hit the brakes harder or you hit the deer. That's the next level that you can use that we haven't really talked about yet. This is why we want to do these problems algebraically in physics, because we can ask extra questions like what happens if your reaction time is too slow. Cool. The other thing that you could do is you could plot this function in Desmos or whatever and think about all the different reaction times and brakings required. So yeah, and maybe if you're on the National Traffic Safety Board, maybe this would relate to some thing you're doing with streetlights and the minimum number of streetlights or something. Who knows? All kinds of weird applications could come out of this. All right. All right. So far, so good. I think we've solved 2.6. Good. All right. Now, what I'd like to do is give you a minute to try one of your own. And I want to go back to, I think it's page 41. And I want to show you another example here. So give me a second. Okay. And then in the green jacket, is it Peter?
Yes.
Yeah, you want to come up here and stand right here. It serves two purposes. One, you're blocking the camera, and two, I need a hand. So let's give Peter a round of applause here. Stand right over there and just catch this so it doesn't fall on the ground. Got it? All right.
Okay.
And then try and just stand like, yeah, lean there like this. Here, rotate this way. Yeah. So if it falls, yeah. So then you might need to move if you can't see because he's going to be in your way there. All right. So here we have this little cart right here, and I'm going to turn this thing on here once I get it in the groove. Let's see if that's blocking. Is he blocking it, Alan, or no? Just this way. Scoot. Yeah, right here. This seat. Okay. Sorry. Does that look like constant speed to you? All right, pretty good. All right, turn it off and hand it back to me. All right. Thanks. So this is going to be our constant speed object. All right. And now this one, I'm going to put this on low. I think we might need a 4-second pulse. This one, I'm going to do this. So if I hit this, it should turn on. It'll go 1, 2, 3, go. Constant acceleration. Oh, looks like I need a longer pulse. Here, we're going to have that back. We need a 6-second pulse. All right. So the idea now is we're going to have one object here that is going to move with constant speed. Then we have another object here with constant acceleration. All right. So watch this physically. Ready? On your mark. Well, let's see here. It starts to catch up, and then it overtakes it, right? Okay, that's good. Let's give him a round of applause here. There you go. That's it. So this is literally the cop and this is literally that cop and the speeder problem that I was just talking about. This is problem 2.36. Now, personally, I like these little demos just because it gives me a physical visualization of what's going on. You have this snail that was going constant speed, just plodding along, and then the cop, starting at the same time, basically comes off the line really slow, but then speeds up and catches up to it. So what we want to do, take a look at problem 2.36, read about it while I erase the board, and then we'll talk, okay? I'm going to spend some time erasing the board, Zoom. Okay. 2.36. You can talk with your neighbor as much as you want at this point while I'm erasing. you're gonna color code your work, I think I used blue for the snail, just in case you're getting prepped. We good? There. What's the first step in any of these physics problems usually? Remind me. It is. What was that? Drawing it, yeah. Units matter as well, absolutely. But let's draw this thing. So to make this match our simulation, we'll have S, and we'll have the cop. All right. The speeder is supposed to be going with constant speed v, but the acceleration is 0. Now we're going to want some numerical subscripts on here. I'm going to let blue be number 1 this time. I think blue was number 1 last time, but I just had them flipped, right? And I should be careful. The 2 initial was equal to 0, but that doesn't mean the velocity of the cop is always going to be 0. Its initial velocity is 0. Right? And then in part A, the words of the statement say, determine maximum separation. I think that's what it says in part A, right? Maximum separation distance. Something like that. Okay. When we see these words, we're supposed to know something in physics, and we got to figure this out. So when you see this maximum separation distance, what do you think we're trying to figure out, or what does that say to you when you're doing this problem? It's okay if you don't know, I'll tell you in a minute if you don't, but if you want to take a guess, try it.
Photograph.
What's that?
You can photograph.
We could plot a graph, and that's a good idea, but I don't want to do that first up. I'm thinking more like in terms of equations, what does this tell us? Or variables, what does this tell us about the variables? Yes.
The velocity of the cop car is the same as the velocity of the snail.
Yes.
At that time.
Yes, exactly. So this is the key phrase that we want to remember. If they're at maximum separation distance, this implies both at same speed. Think about it. If the cop is going slower than the snail, the cop is getting farther and farther behind. If the cop is going faster than the snail, the cop is catching up and closing the gap. So at this point, in equation form, we would say give me a second. Maybe I'll leave it like that. In this case, we're saying if the speeders, or sorry, if the cop's final velocity, let's write the words there too, so it's more clear. The velocity of the cop should equal the speeder's velocity. At that point, that is the transition between gaining ground and losing ground. Okay, what do we need to compute? If I said d is that distance, how would I get that distance? From our standard variables that we have in our 1D kinematics. you agree at some point, it's gonna look like this, where the cop is say right here? And the speeder is way ahead? Right? If I want the distance between them, let's do that in some other color. How about green? If I want the distance between them, how am I gonna get that? Yeah, something with the X's and take a subtraction. I couldn't quite hear you because it's, math and all that, but whatever. In this case, it should be delta X of the snail, which I think was number 1, minus delta X of the comp, which was number 2, right? Something like that. And I think that's what you said back there. If not, you were probably pretty close. Thank you. Now think, why is it okay to use distance instead of displacement for this problem?
Positive?
Everything's going in the positive direction, no turning around, right? So I'm trying to emphasize that. In general, delta X means displacement. In general, you might have to worry about absolute values.
Would it be safer just to always put the bars in front of the X's in case?
Sure, but then that could also make it harder to understand when you're first doing it as well.
Okay.
But yeah, you're absolutely right. So in this case, why don't we just make a note every time this is true instead of doing that? Note. Distance equals displacement if never reversing direction, which is true in this problem. So how about we just put that note anytime we put that note, then we don't have to worry about absolute values. Is that good? Yeah. Yeah. All right. So that's part A. That's cool. What's part B? Let's read part B. What are they talking about there? In part B, it says, how far from the origin is the cop when she finally overtakes the speeder? So part B says, cop finally overtakes speeder. If that's true, if part, right, in this case, if the cop finally overtakes the speeder, what is that piece of information telling us in terms of variables and equations?
Same distance.
Yeah, and so this is the problem where you say delta x1 equals delta x2, right? Now, in this particular problem, what is true about the times? Are these two vehicles driving for different amounts of time or the same amount of time in this problem?
Same time.
Yeah, so for this particular problem, we might make a special note. In this problem, both cars moving for same amount of time. Is that true in both part B and part A? In part A, are they traveling for the same amount of time? Yeah. In part B, are they traveling for the same amount of time? Yes. Now, to be clear, the amount of time in part A should be much smaller than the amount of time in part B. But we do know that T1 equals T2. So sometimes what we'll do when this is the case, we'll say T1 equals T2 equals T, so that we can clarify we don't need to worry about the subscripts on time. How are you feeling? Okay? So now, if you want to solve this problem and learn about parts A and B and work your way through it, what should you do next? What are the next steps? We've got some pictures here. Obviously, you're probably going to want to redraw your picture for part B because it's going to be slightly different, agreed? But what would you do next? After you have a picture, we've got some symbols here. What would you do next?
Just your knowns and unknowns.
Yeah, so we make two tables of knowns unknowns, right? What's next after that? Every time. List some equations. Outstanding. Then what? What's the first ones you should plug in? Plug in the special, anything that was zeros, right? You can also plug in the numbers, but the zeros is crucial. Make sure you remember to do that. What was the next step that I did? You remember? We had some equations. We plugged in the zeros. What did I do next? Do you remember?
Find the equation with the least amount of unknowns.
Yeah, so do that. I'm going to call it like checks and question marks. Do you know what I mean? That step that I did? Just going through and kind of looking for what's got what. Now, I guarantee you, this one's going to be a little bit harder than the last one. Not outrageously hard. And I can also guarantee you this. On this page, they get harder as you work your way down. And so if you want to make sure you can handle this type of problem, this is called a multi-stage problem. You want to do questions 2.36, 37, and 38. Even though they all look the same, they get nasty. All right, let's take some time. Let's do it. Alan and I, we can start circling around and try and help you. Talk to your neighbors as much as you can. Let's see how you do. Right? All right. Nice job. Nice job. Yeah, everybody was rocking it. Yeah, yeah, for sure, for sure. Okay, got some ideas? Okay. Feel like you got an idea or a question? You look like you could talk. Okay. Good. Okay. Also good. Idea?
Yeah.
Okay, I'll come back and ask.
Yeah. Yeah, just looking at that. I'm also trying to catch up with other stuff.
Yes.
No, I'm sure it goes wrong because last time I want to figure out the testing first.
Yeah.
But I don't know, like I have other classes, like hard to like do that class. And like, yeah. Okay. But I think I want to probably work on stuff for catch up.
Is it good on your list? You're still working on it?
Still working on it.
Okay, okay. How about you? Yeah, yeah, you probably just have to scratch out the, or you could just start part A here, right? This is like the introduction. Then just start part A there. Just start over. Cool. You want a laptop or anything? You good? Okay. All right. You took a break. That's cool. I understand. Okay, you know where to get back into it, right? 2.36, Bill. Okay, cool. Making some headway.
Yep. Check. Smart.
Okay, okay. Somewhere? What's that? Not yet? Specific questions or should I just feed? We're working on part A, okay? So rather than trying to think too much, I'll get that out. Or you got it?
I got it.
Okay, Alan's got it. Rather than trying to think too much, the idea is we want to let the paper do the work. So just get your list of knowns, list of equations for the two, and then do the check mark and question mark, just to get a feeling to see if one of those equations is going to help us usually what happens is there's usually only one equation that's kind of, it's gonna work out. Take that equation, start there. The one with the fewest questions. So that's my advice, is follow that procedure all the way through. Cool?
Yeah.
And without thinking, because you can always reread after you get all that down on paper. Cool? Change velocity. Change velocity is zero. What's that tell you? I would bet you shortcut. I would tell you, never base on
You read that, it doesn't say anywhere.
You read A equals zero.
Yeah.
So you probably have gotten it. So the trick is try not to overthink it, flesh out equations. If you miss that, sometimes writing the equation will give you that insight. Good check in with the Zoomers real quick. Just checking to see if anybody here on Zoom has any questions. You can throw them in the chat if you want, or you could try just talking, whatever you think is easiest. I'll try to answer if you haven't. And obviously, I'm assuming you would use the solutions too. So like if you get stuck, use the solution for this first problem, right? It's okay to use the solution if you're stuck and I'm walking around and I'm not on screen, okay? All right, I'll just come back in a minute. Okay. All right. All right, doing all right? Yeah. Okay. Yeah, understood. It's probably not going to be the same equations or whatever, but the same process, right? You're looking for whichever question. Let's take a look at it.
Let's just, we know that this max separation is so
So that's a number that we're going to know. So we can put it in that scale with a B and you put it in
that makes sense. Yeah.
So it looks like you don't have that elements that you actually do. And so whatever A is, this one is going to be.
So I recommend probably, I'm not sure.
Only this one.
Might not get an answer from part C, but that's probably.
Do we know that line? Yeah.
Send me an email, send you my general schedule.
I don't see the time. So time is a question. Cool.
Just give it a shot.
So next up, what's your next move? Write the equations, do the checks and questions. What's up, Dominator?
Not much.
That's cool.
Let's check to make sure it's good.
Oh, yeah.
Don't get,
That's right, that's right. All right, wait a second. Now, close a bit. Right, yeah, so write the equations, try not to overthink it. Get those equations on the page, do the check and question mark, right?
Yeah.
Yes, that's what I would do next. Don't think, right. Okay, and then when you're writing, or after you're done writing the question, check. That's when you can start thinking. Cool. Yeah. Up here in the middle, still good?
Yep, I think I got it.
All right, all right. Don't forget, you can check on your phone. Or whatever. Still good up the front here? Yeah, you doing? Getting into it? Yeah. You're getting your list. Next up, you're gonna do what? Yes, you're on. Good. Nice.
Let's put the one that's on.
Yeah. So that's why I feel bad about that first problem that I put them left, right, because I set a bad precedent the whole day, but. No,
No, it was just me.
Okay, all right. Wait, how you doing back here? Headway? Getting the equations? Yep, all right, sweet. Hopefully this becomes one way where, like, you see the problem, you always have to check, they give you the question, find out what you're looking at, right? Yeah, you get really fast. All right, make some progress. Okay, all right. So what's the, what was the? No. Yeah, you gotta do that subtraction, right? So you got one of the distances. You found the time, that time is relative to both, as you index distance, which I did. Notice you lost a subscript, right? So that probably would have, yeah, so I think what you found. Right, but it's not, so this is what I'm saying, it's like, if you have a subscript two always, right? It's less than, see where you're at. Well, that's what we actually have to answer one of the questions. And so, which one should we be?
The max distance.
There you go. It's like this is the same equation. So I think, you see what I'm saying? I think, so you call X1 the speed. Okay, so this should be X1. It's speed. And so if you're getting that, so. We'll discover over time. It's easier to always write extra subscript so it's clear. And then you have to have one extra step. Sometimes T1 equals T2 if you don't. But it's better to default having subscript and then think about, can I do that? Just in my experience. Subtract off. So you gotta figure it out. That's the one that doesn't need the subscript, right?
What did you get from the final?
So you need an equation for the other x. Yep. Okay, so then, yeah, and then what I would do is, again, keep subjects on. Maybe, I don't know if you saw that, but I not only put subject, but I also sometimes put words, so like top, two, speed, one. That way, the less you have to think, you review these notes, easier for you to study the test, better have. How about you, doing all right? Okay. Checking in with you, how you doing?
It should be, I'm trying to, these are all numbers that we're not like, we're just using symbols, right?
Yeah, so you can use the, and at the end, I think it's the use of numbers, but whatever.
At the end, yeah, I saw some over here, but
Oh, yeah, did you guys notice? It's not 30. The velocity of the snail is not 30. It's speed V in a 30-mile-per-hour zone.
Yeah.
We don't know what V is, it's just V. All right, anyways, okay.
It's a little bit fun at part C.
Yeah, later on, I tell you it's 20 or something, but yeah.
yeah, it's not constant, right?
Well, that's the question I have for you. Why do you think it's constant or not constant?
There's no mention of it.
Yeah, if I say I'm driving at 50 miles an hour, what speed am I driving at in 1 second? I don't tell you anything else. I'm driving from here to Compton at 50 miles an hour. How fast am I driving? Percent? No, just, yeah.
Oh.
50, right? Doesn't that kind of imply constant speed?
Yeah.
So that's the thing. When you see that, if somebody says you're driving with this speed, that implies constant speed.
But right here, because from, I mean, We know later on, right? But from here, does it say it is considered?
It does. It does because that's the implication unless you need to tell, right? If I tell you you're driving at speed V,
That's it.
that means your speed is V while you're driving.
All right,
That means constant speed V unless otherwise specified.
all right. Yeah, I get it. So
It's a subtlety.
so like in a test, it's the VR.
Yeah, you could raise your hand and ask a question. Say, is it, I'm assuming this is constant speed. Is that correct? You could ask me and I would come over and say, I don't know what you think. But usually, right, yeah, if you would say, in this case, that's one of the reasons we're doing this together now. Is that is an assumption we're supposed to learn how to make a physics question. Good? It's very not on there. Good question, good. Good enough?
Yeah.
Good, thank you. Okay, so get those labeled, then give your equation. So is it the same time as what we already have? So that's the joy of part B, is like you got to figure it all over, right? So like, it seems like these don't seem too hard until you realize basically. But then you'll be used to these words. Is that good?
Yeah, so then that's what T1.
So you'd still be the same, but just not the same as part A. See what I'm saying? In part A, the time is gonna be like a half an 4 seconds. And so, right, we know that T1 and T2 are gonna turn out to be.
We know that for just for part eight, just per eight, that velocity is
But
usually the same.
it's not the same.
So we don't have to label it for snow or hot. And we know the time is gonna be the same.
That's still true. Yeah, so basically.
Is eight. Snow is zero. Because the snow, he's already driving. at constant speed.
Even though it seems really bad right now, the idea is basically you're gonna get so fast at writing it out. Eventually, you'll start doing checks.
Well, so A is zero, so we don't have to add A on the snow, just on the top.
Yeah, yeah. Oh, this is. Oh, this is a good way to start. B if this problem. So, but by writing out the checks, the question right now is full. Good. All right. Everybody get somewhere? Yes. All right, you got your equations? Yeah.
Yeah, I'm just.
I like this, that's correct.
Oh, okay.
Then the only question is, you need T. Which equation can get you T up here? We don't know the times. Right? In the last problem, we knew the times. In this problem, nothing else. Look, I don't see T in it. The last problem, T wasn't. This problem, T. So erase that T and then take a look. Let's see.
I should have to say this equation one is a problem.
Yeah, because then you figure out T. Yeah, I agree. Once you know T, you agree, then you can get the
Yeah,
other.
oh, okay, now I see what you mean.
All right, good. What do you think?
Yeah, whatever.
This is correct. But do you agree? You didn't plug in you agree that the initial speed is V. The final count is also V.
Yeah.
This is also V.
Yes.
Well, V and A are known. If you just plug in, right here. That's the answer. So then wait a minute, this is, oh, we don't want to solve for V's, we wanted to solve for V's.
Oh,
So it's literally just combining these two terms.
yeah, I combined them
Yeah.
and then I took out the variable.
Oh, yeah, so there's the answer. That was it.
E squared over
V,
V.
1/2 V squared over A. That was the answer. Nice. Oh, shit, right there. That's the answer. This was unnecessary.
I thought we were
Put a
looking
box.
for the velocity.
Yeah. So that's the trick. remember, once you get towards the end, that's a good time to reread. And I know it seems silly when I always write that WTF, right? But the idea is for this situation right here, you're like, what the heck am I trying to find? That keeps you on target when you get to the end. Like, look up, like, what am I trying to get? This. So notice you have it right there. So that's why it's okay. Is that good? All right, outstanding. Make it headway?
Yeah, I kind of lost a little bit because I put a known in the acceleration, but then I said wait.
Okay, cool. All right.
You guys just gotta solve.
Yep. What's up?
Fixed it.
Okay, cool. You're on your way then?
Yep.
All right.
Okay.
Okay, getting it done?
Yeah.
Check the units. Makes sense. If it's, well, we don't write the units on the breaking, so you can check that, agree?
Yes.
And let me, and then you
Because
can
it's
also check.
supposed to be the distance, so it
So
must
this
be
could be
nine.
this. Check it out. Usually meters per second, but
Oh,
whatever, who cares?
and then let's just see. Acceleration. That's the letter I-
Multiply by the reciprocal, so you don't accidentally screw it up, right? I like to do it all on paper, because let's face it, it's easy to make mistakes, right?
Yeah.
So,
Let's see how, That's what it's about. So, yeah.
So at some point, you probably need a break. This is a good time for that break. You got the solution here. If you want to finish it up, that's cool too. I'm gonna keep circling the room here and erase the board, but maybe I'll say this really quick. You've got the solutions, but the strategy here was this. Whoops. The idea was you could use in stage. Let's see, for the cop, the speeder and the cop. So for the speeder, which is number one,
I use
then
that.
with delta x1 equals v1c, then we don't need a subscript.
Yeah, you solve for T.
So did you use this one?
This is part A, I should mention.
Which is the divide that you see.
So with this one, the key was here, I know that this is going to turn into V. I know that V initial was 0. I know that this was A. I could use this equation to get the times. From the time, then I could plug that into these two equations and get the two delta x's. And from all that, we get D. I think in this problem, what was it? Delta x1 minus delta x2, and you could get it. So that was part A. Part B is pretty similar, but you have to start all over. So again, this is a good time to take that break. I'll let you do whatever you want. All right, so I know it's kind of approximately time to get back into it. I wanted to kind of review a couple of things here. So I wanted to run this program again and kind of get a look at it. But in part A, what were we doing? It was supposed to be max separation, I believe, right? Now check this out. Let me do this. Let me get down into here. Make this a little bit bigger. Right now, I can change this like this. Think about what that while loop statement says in line 155. It's saying when the x component of ball one's velocity is less than or equal to ball two, basically, when one of them is slower than, and I think I have my ones and twos switched here from how we did it on the board. But the idea, it's saying, look, run this simulation until the two balls have the same velocity. That's effectively what this sentence says. It's saying while they're not equal, run the loop. So this is saying basically as soon as they're equal, stop the loop. So let's go take a look at this one. This is a little different than what we did before. This is part A. When I run this, okay, and again, I don't know if you can see this. This is supposed to be the cop. Notice the numbers are off by a factor of 10. So my apologies for that. I probably should have thought that through. So when I run this one, we've got the cop and the speeder, or C and S. When I do this, look at that S car go. Good old snail joke. Never mind. Now take a look. Look carefully at when these plots have stopped. Right? And let me clear the annotations here. Notice in the plots, this is D, the maximum separation, right? You could come over here and punch in some numbers. And now that we've coded this, you could actually get numbers. It looks like in this particular problem, the distance of separation is 4. Maybe yours would be 40 because we're off by a factor of 10. Look at the velocities, right? You want to stop the code when the velocities are the same. That's what we were doing. So we could see this. Now I'm going to go back and run the code another time with a different while loop statement. Give me a second. What was it, line 155?
Yeah.
Most of this is just comments, right? So, right, if we change this to ball.pause, right, that's saying when are the balls located at the same spot in the x coordinate. Now, I'm going to take this back down a little bit, run this program. Okay, when we run this one, it's going to run longer. And we see it stopping when they hit the same spot. Notice the following. What is true about the red area here compared to the blue area here? What do you notice about those two areas under the VT plot?
They're equal.
They're equal. Think about it. You could take this triangular piece, cut it, flip it upside down, and shove it in there, and you'd have exactly the same rectangle, right? So this is just trying to tie it together with what we did last time with the graphing. So if you can understand a problem in these ways, right? If you can draw it, if you could do algebra for it, or calculus, or whatever, if you can plot it, and if you can code it, you probably really understand a problem. And this is kind of a microcosm of what modern science is all about, right? It's not enough to do problems with paper and pencil anymore, but maybe you could do one case with paper and pencil and use that to check your code. Then you could write a code and simulate it, or you could plot it using Excel or Desmos or something, right? So there's different ways of looking at these problems. And if we understand all of them, that's a much stronger understanding, and you know the interrelationships between them all. Any questions about this while we've got it up? That's the plots. All right, you could think more about it when you're doing your homework and look at the slopes and all that. All right, so that's one way of handling non-constant acceleration, multiple stages. All right, let me do this and this and this. And smash this remote. And let me get some screens up and lights up. Okay, so now I think we want to go to separation of variables. Does somebody have that page in the workbook? We're going to table the contents. Or I think it's like another 10 pages down. 49, check page 49, will you? Thanks. Yeah, 49. So separation of variables. All right, so we're going to try and use calculus. Now, let's see if I can organize it this way. You probably know this equation, A equals dv dt. That is a full vector equation. But we can simplify this in 1D to A sub x is equal to ddt of v sub x. And then because I'm going to be lazy, I'm just going to say A equals dv dt without any arrows on it, okay? So it's basically, to be clear, it's really a vector equation, but we're just going to look at one component. And I'm not even going to write the subscript x for this part. Everybody okay with that? Okay, so in this case, A equals dv dt is called a differential equation. And again, you've got the notes on the page. You could just annotate page 49 if you're reading along, right? You don't have to write all this from scratch, right? So now, dv is called differential velocity. When you have a d in front of it, it's not velocity anymore, it's the differential velocity. Similarly, dt is differential time. Maybe I'll take those quotes off so I don't have all these quotes. Differential time. All right. Now, what people will often do, separation of variables, so we could get the t's on one side and the v's on the other side. Now, where am I getting this from? This equation is differential velocity and differential time. The idea is if we can get all the dt and any t's that go with it on one side of the equation, all the dv's and any v's that go with it on the other side, we can literally just integrate both sides of the equation and we'll have a t integral on one side and a v integral on the other side. So we're trying to separate the variables into two easy integrals. Okay, so we'll do a quick example. Let's let A equal a constant. If we have constant acceleration, let's separate the variables. Well, in this case, separating the variables is literally as easy as multiplying both sides by dt. Do you agree that if I just multiply by dt, I've got anything with a v in it on one side, anything with a t in it on the other side, and this is just a constant? Okay with that? I'll try not to write so low on the board, but I'll try and, it's tricky with Zoom. So if you need to, let me know. Can you see that all right or not? Just fairly, okay. All right, so in this case, we can integrate both sides. And when I integrate that in a physics class, I don't know if you remember, I said I want to go from initial to final on both sides so that I don't have to try and think about the plus C from calculus class. All right. What do you get when you integrate dV? Let's go up here. When you integrate dV, what should we get on this side of the equation? Yeah, V evaluated at initial and final, which somebody said it is going to be V final minus V initial. How about this? I'm just going to move this. Just so I have some room to work, sorry. Okay. Great. How about on this side? A is a constant. What are we going to get? T. A pops out. I get T evaluated at initial and final. So far, so good. At this point, I like to do something special. Usually, what's a good initial time? 0. Similarly, we could set T final. If there's only one time in the problem, I don't need a subscript. So at this point, I can get rid of that integral. Or I mean, that subscript. I apologize. Let's rewrite it. We get V final equals V initial plus AT. The most boring problem in the universe because we already have that answer memorized, right? But there's something I wanted to point out to you. This is technically the solution to the diffie-q. So again, we have all the parts of a differential equation shown on the board. We have a differential equation. Typically, we're going to have that coming from a physics equation. So physics usually tells us differential equations. However, in practice, we don't want to know the differential equation. We want to know the solution to the differential equation because this ends up being useful in a wide variety of applications. Does that make any sense? So we've got these terms, differentials. You want to separate the differentials and any associated variables, do your integration to get a solution to the diffie-q. Okay, that's just all the terms. Any questions on the terms or this work here? Yes, go ahead.
It's kind of confusing that it's A. I mean, is that on purpose or
What do you mean?
the A? Like, that could be just like C instead.
Well, in this case, let's go back to where we started on this problem, right? The physics definition was A was equal to dV
Oh, I
dt, and that's why I chose A.
I see what you mean.
You know what I'm saying?
Yeah.
And then in this special case, A was a constant. So the combination of this differential equation for physics plus this constant is what allowed us to get to this solution.
I get it.
Now, the only thing that's really different about this is sometimes we will call this, look at this, check this out really quick. Do you agree, if you tell me the time to plug in, I can get the velocity at that time? So strictly speaking, this is the same thing as V of t, or velocity as function of time. Some interesting noises. Okay, whatever. All right, that's cool. So far, so good. Now, we could actually do this again. Okay, this is the velocity as a function of time. That's the solution. That's great. Let's see if we can take this one step further. Let me go over to board 6. All right. We know another equation. Velocity is equal to dx dt. Agreed? And again, I'm ignoring the vectors and the subscripts, just doing this. Well, at this point, I want to point out, we could take this velocity right here is velocity as a function of time. Think about it. If you know a small amount of change in time and a small amount of change in position for anywhere in an object's motion, you would get the velocity at that instant. So what we could do is we could take our velocity as a function of time and shove it into here. Let's do that. Our velocity as a function of time was v initial plus at. That should equal dx dt, right? At this point, I want to group anything with a t in it on one side of the equation and anything with an x in it on the other side of the equation. Fortunately, do you see anything with an x in it over here? So in this special case, what do I need to do?
Just divide by 1/t.
Yeah, or multiply by dt, however you want to say it. So do you agree we get v initial plus at quantity times dt is equal to dx? So far, so good? Now, this equation is separated. I've got the t's with the t's, and in this case, the x's with the x's. It just does not have to be any x's. So at this point, I can integrate, right? Initial and final. Initial and final. Is the initial a constant?
Yes.
Yes. This is not v anymore. This was v. The velocity is a function of time. The initial, there's only one velocity at the start. That is a constant for the whole day, right? Right? Your initial velocity is whatever it was when you started. That isn't changing. I don't know if that made any sense. So A is a constant. So when we do this, oh my gosh, we're going to get v initial times t plus 1/2 at squared. And I want to put this in, evaluate it at initial and final. You may say, that's stupid, dude. Well, just trust me. On this side, I'm going to get x final minus x initial. Do you kind of see that? At this point, now I want you to plug in the limit. This, the initial limit goes to 0, and this final limit will go to t. The trick is, it's strictly speaking mathematically funky if you have 0 and t inside the integral. We don't want to have t in the limits and in the integrand. That's just bad form mathematically, all right? Makes me want to puke. So we don't want to do that, right? What we want to do is shift the variables after you do it. So in this case, always check. Does the 0 limit drop out in this case?
Yes.
Yes. The most common mistake students make on this type of problem is not checking if the 0 limit drops out. That's the most common mistake. That and not separating. Okay, so in this case, oh my gosh, out of all this, feeling good on this one? Okay, now we see this is the solution to that differential equation if this all was assuming A equals a constant. Agreed? Well, our whole so we did the easy case when A was a constant. We've been doing this for 3 days now, a week, whatever. Now we want to see what happens if A is not a constant. Can anybody think of some sort of situation where the acceleration would not be constant? Maybe from lab.
Man.
What's that?
I mean, what about like a broken car?
A broken car.
Yeah.
Well, I don't know. It depends how broken. Because if it's really broken, the acceleration would be 0 and it would stay 0, right?
Yeah.
Just drag when you.
Drag, air
drag
resistance,
something.
man. It's a real drag. There's 2 different types of drag. So I want to talk about drag really quick. And that's the one I wanted to talk about. It's not, you could talk about a car as well. So new example, drag. There's high speed drag and low speed. And really we should be talking about Reynolds numbers, but we're not going to. It turns out, I know I'm going to skip ahead here a little bit. You don't need to write this down. I just want to inform you. I think I use alpha sometimes here. So the idea is this is a force. This is a drag force. Now just humor me. I'm sketching out why you should care about separation of variables here, right? There's a thing called force. We haven't talked about it yet. We'll learn more. But the net force, like if you had a ball here and it's dropping, and there's some gravitational force here, and maybe there's some drag force here, I'll call it R for resistive force, right? We know this thing is going to accelerate downwards, right? It's going to speed up going downwards. So I could choose to draw my coordinate system however I want. More on this later. Again, you don't need to know this. This is chapter 5. We will go over this in detail. But the idea is I could get an equation out of this that says mg minus r equals ma. I could divide this equation by m and get g minus the resistive force per unit mass is equal to a. Now, why am I bringing this up? Think. This r equation is going to depend on velocity somehow. So instead of having velocity or acceleration that was a function of time, here we have acceleration is going to be a function of velocity. So you could use these equations and you could do a similar thing, right? You could say dv dt is equal to g minus resistive force over m. At this point, we could plug in, let's just pick a model. How about, let's do high speed for some reason. I just want to point out, here's an equation with v's on one side and v and t on the other. If I want to do this, I want to ask you a question. What if I just cross multiply by dt? Is this going to be easy to integrate? Should I just slap an integral on this and do it? What do you think? No, the v's are not with the v's. This is not separated. The idea here is, sure, you could try to do this integral. This is a legal mathematical statement. So is this. This is a legal mathematical statement. The problem comes, do you know what v is as a function of time? So we got nothing to plug in. The whole point is to figure out v as a function of time. So we don't know it. I can't plug anything in. I don't know how to integrate. Bad monkey. Right? Where's my eraser? So this is not going to work. So let's try it again. I got dv dt is equal to, what did I say? G minus, did I use what? Alpha v squared over m? What should we do? I want to integrate it, but first I have to separate it. Any ideas? Multiply by reciprocal? Okay, sure. Which side? Okay, so what should I multiply by over here? Okay, so it says multiply this side by m over alpha v squared, like that. Which term? This one, both of them, or what? Whoops. We could do this, right? Except if you do this to one term, thank you for catching that, we'd have to do it to every term. And then we're starting to run into trouble. So that's a good idea. It's not going to quite get us there.
What you can do is probably subtract g, and other side is a constant, and then multiply.
So he's saying subtract g, put it over here.
Yeah. Since it's not a function of time or velocity.
Okay, that's still legal, but now what?
Now you can multiply the v squared.
Nope, that's not going to get the job done, because then it's going to appear in this one, and you still have t's over here. So when you cross multiply by t, it's not going to work. Bad idea. Nice try. Yeah.
Maybe try adding alpha v squared.
No, I'm going to show you. First, multiply by dt, just like before. Now, everything with a v is in here. what could I do to get all of this crap over there?
Divided by the same.
Divided by all that crap. You see what I'm saying?
Yes.
And this is the one that everybody has trouble with because they're trying to do stuff and I don't know why. But once you see this trick, you're like, oh, that's the trick. Okay. Do you agree at this point, everything over here is going to drop out? I've got T's on one side, B's on the other side, and I got a nice, pretty U sub to do. Cool? So this is the main difference between how they teach it in calc class, where they always give you like an easy polynomial or something, and it's just, oh, it's so easy to integrate. Here, there's a physical reason for doing this problem. We're trying to understand something in reality. And then that means the equations sometimes look a little goofy, but we must always separate before we integrate. So far, so good? All right. Now take a look at the example I showed on page 49. I think there's a plus sign error in there at the last step, isn't there? Yeah, I think there's a plus sign error right there. I got to fix that. The last two lines should say V initial squared plus. So fix that minus sign to a plus. And the last two lines in that example, sorry about that, right down here, that should be plus symbols. And the last two lines of the. But notice there's an example where there's V's and T's in it, and you got to separate the variables. Is everybody okay with that? Hey, Hank. A common question at this point, or well, any questions at all? What use does this have? Why are we doing this? That's a good question, right? So that's your notes. Flip the next page. If you flip the next page, I showed you the bad monkey mistake. You could read that if you want. But also, you can see most of the differential equations that we use. There's 10 different examples of differential equations we might use in physics 1, 2, and 3. And I even left a couple out there. So we can use this for solving the hydrogen atom and deriving the different energy levels in the periodic table. We could use this for understanding drag. We could use this for understanding circuits, a number of different applications. We can do rocket physics. That's number 10. Oscillations with masses and springs. So there's a large number of problems that we can analyze using this one technique called separation of variables. All right. So what I'd like you to do is try some problems on page 51 and 52. And I want to note the problem, the wording at the top of page 51. The problems on page 51, basically you can multiply by dt and integrate, same way that you did in calculus all the time, right? The problems on page 52 require you to separate before you integrate. Did that make any sense at all? Basically, most of the time you're used to just integrating. Sure, page 51, you can do that. Now, to be clear, when we did this earlier today, there were two main problems. Sometimes people skip right to problem 2.55. 2.55 is going to punch you in the face. It's brutal. I recommend starting with problem 2.53 if you're at all uncomfortable with this. The other thing is, make sure you read, right? People were trying to make these problems and were doing this crazy, like they didn't read the problem and read that some of the parameters are constants. So they were trying to do integration by parts. Why everybody wants to do, I don't want to do integration by parts if I'm happy. So read the questions, try 2.53 if you're feeling uncomfortable, use the solution, ask questions if the solution doesn't make sense. And then you could move on to page 52 and do one of those. And that's chapter 2, we're done. Okay, let's do it. Do a couple problems and then I'll show you something on the way out in like 15 minutes, all right? Let's do some work. Pick a problem, have the solution out, go to work. Oh, I'm gonna erase the board here. I'll leave this one up just in case. All right, talk as much as you want, work on one of those problems. If you're not sure, start with the first one on page 51. Make sure you know what's constant and what's not. What do you think? You get a feeling, right?
Yeah.
Okay, good. Yeah. Okay. Okay. Same with you as well. Okay. That's some ideas here.
That's where it's gotten order.
Yes, exactly, right? There's a physical reason for it. Hopefully that makes it more fun to learn.
Yeah, it does.
Okay. What do you think? How you do? Good question, right? Yes, that's a good plan of attack. Okay. Okay. So it says the initial is this constant. So basically, oh, okay. Zero. So like the initial is necessarily zero in the solution in a bit, right? Yeah, that's what I'm saying. Go to A, go to J. So when you finally work your way up to X, it should look a little different. And then we'll be acceleration is not constant, but just as constant. Good. Good. So what do you think back here? Got some ideas? Yes, that's exactly right. It looks weird, it feels weird. In the problem up there, we have B's, A's, and T's. Now you have J's and A's. So what? Cool. Yes, yes, so exhibition, yes, exactly. Yeah, so up there on the board, right, we had constant A, so it took us 2 steps to get to X. Now it's probably gonna take 3 steps, because you use this equation to get to A as a function. Then you go to B as a function. Yeah. And then you go to X. Good? Are you good with that too? This is an equation, right? So suppose, look at the board, right? See how before we started with A equals B dt? Whatever. Now I'm telling you, J is B A dt. So basically, it's a similar process, except instead of B's, we've got A's. And instead of A's, we've got J's. Do the same process, but you'll see the process, instead of having just 2 steps to get to X and T, there's going to be 3 steps. You got to integrate to get A. And A is not a function, or A is some time function. Then you repeat this procedure, but A is some function. And B is some different function. Okay. All right, cool. Have a shot. J is a constant. Separate, integrate. And you can also open up a solution too. That doesn't have to be, right? Give it a column. It's literally the same.
I got it. We're gonna make this as.
So B time will be D as a function. A will be A.
Yeah, because you know how like for the.
And then I think this column I chose to call A initial base 0.
Oh, so
Without acceleration.
yeah. That was.
But yeah, whatever. You're I'm just letting you know. That's good. What do you think? Yes, yes. Oh, wait, A initial is not 0. It's A0. So it's all right except for plus A0. And do you agree it looks exactly like the velocity equation up there, except the B's and the A's and the A's and J's?
Yeah.
And it's exactly this, it's like, it's like, okay. Correct. And you integrate it. Stick on your initial minus. Good job. That's good. What do you think? Yes, 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 yes. Okay, that's it. Don't overthink it. You're done, guys. You got it. Exactly. Getting there? Got it? Okay, okay.
Put it in blue, so
Give me a second to think.
T, I, or the initial be zero.
Okay, okay. Yeah, following along with the solution, is a great idea at this point, right? Because we're trying to get used to this technique. And then when you write it out, that's good. That's good. Usually we put the constant on this side of the DT, just out of formality. It's usually constant. That's right. Yes, that's it. This is it. This is correct now. What you
Now
just
I
wrote now is
understand.
correct. Yeah.
So with that,
Yes.
so
Yes.
this was so
Yeah, this
incorrect.
is
I
it.
just forgot
This
to
is,
do
this is
that.
it. This is it, right? Do you agree it looks exactly like this one? Doesn't that make sense? Except now V is an A, J.
I don't have to.
Wait, so
It's the same process, except now, think about it. Acceleration is a function of time. Acceleration is changing linearly with time. If you have a constant jerk, that means your acceleration is changing at a constant rate. So your acceleration is some initial value plus a change times time. That's totally good. Now see if you can work your way all the way up to X. Cool? Yeah.
okay, yeah.
Because now you got A, now you can repeat and you can get V, and it's going to be some ugly equation. Then you can repeat and get X, right?
Or the-
You know this equation. You can start from here, except now you have an equation for A.
Yeah.
A0 plus JT. Shove it in, you get a slightly different integral. And then you get to this step. You could do it again. Or you can have a new function for V that's not quite the same as before. A little bit different. Good? Yeah.
With a final minus a initial.
What's that?
What do I do with a final minus a initial? What does that mean?
Remember, what was the step that I did previously? Look what I did. I solved for, in my problem, I solved for V final or X final. What are you gonna solve for in this problem?
It's all, it's a nice determinant A.
Yeah, so A is a function of time is it A final or A initial?
It's A, right?
Which one?
Crap, it's hard to understand.
I know, there's a standard substitution you're supposed to know. You can solve for, in this case, it's solve for V final, and then you can interpret V final as V of T. So now you are doing an A integral, so what do you think you're gonna solve for?
I already solved,
What are you gonna solve this equation for? A final.
Let me write it down real quick. Just make sure it makes sense. That should be zero, right?
That's gonna go to 0 now, or T final goes to just T, right? A final, look at this, if you tell me the time and the initial velocity and the jerk, you could compute the final velocity, or final, I misspoke, it's the final acceleration. A final is A of T. A of T. It's not A T, it's A of T. Yes, right, A final is A of T.
Say final.
I hear you're saying
This A is a function. Tell me, T initial, so J as a function of time is equal to A initial plus J T. With T final. You agree with that statement?
yes, that's what I had.
That's all it is.
A initial,
Don't overthink it.
it can be zero.
If you want acceleration as a function of time, get A final. If you want velocity as a function of time, get V final. If you want position as a function of time, go check it.
X final.
Is that better now?
A is zero.
So, yeah.
It's just something weird, right?
Oh, yeah, yeah.
It's just a variable, but it doesn't explicitly say
Yeah, that's it,
zero.
right? That's it. Okay, all right, cool.
Yeah, I get it. Thank you.
That's part A,
Add it.
and B, et cetera.
Yeah.
By the time you finish this one, you'll start to see the pattern and start to feel a little better, because again, it might still need to do another. Cool?
Yeah.
We think I saw it. Is it somewhere? Wait, wait. Get X to T yet? That's the next one, right?
B part C.
Yeah, yeah, do it.
I have a question for Sam.
Sure.
I get you all the abbreviations for you.
Yep.
But how do you?
Okay, first off, the initial acceleration is not zero. So when you
Yeah.
integrate the A, it should be A final minus A initial. So A initial in this case is some number. T initial is what's less than zero. Right?
So you can plug in a 0 for T.
Yeah, but this is driving me crazy. That should be A final minus A initial. Is that good?
Yeah.
So whatever is the constant,
You put a zero there. Usually we rewrite T sub final as just T. Now, yeah, exactly. Now, okay. The trick is, if you want acceleration as a function of time, you solve for A final. If I want velocity as a function of time, I solve for V final. If I want position as a function of time, what do you think I would solve for? X final. Got it? And so you solve for A final, that's the answer. Cool? Because A final literally means, what is the A when you plug in the final value of T? That's what it means to be a function of time. Is that good? Is that what you needed?
Yeah.
What were you saying?
I was just saying that, because we are like saying like you find, or we're plugging in the acceleration final, whatever you found.
That's right. That plugs in the next step
And then it goes
to,
keeps on
yes, it just keeps building.
Is that just because to make them connect, or is there?
Well,
is there a purpose?
it's because in this problem, if you have constant jerk, there's only one equation for the acceleration as a function of time, and it's the one you wrote down. So for this problem, we could use this A. For this problem, we'd have to use this A. You see, for this problem, it'd be, yeah.
Okay,
You got it?
Yeah, and then the constants, they transfer over, right? So you don't have to.
I know we're getting close to time to go. You guys keep working for a minute. I'm going to show you something on the big board and then get you out of here, okay? Keep working. Don't forget, I'm in Mesa Center tomorrow. You can come in and try and get some help and get some extra credit. It's basically this Tuesday, this Saturday, and then I think 2 weeks from now, Friday and Saturday or something. It should be close to your test. It's in Canvas, if you forgot, the extra office hours in Canvas, if you forget the times, right? Because nobody wants to remember everything right now, we're tired.
Oh, is Mesa Center open on Saturday?
They're gonna unlock it for me,
Just.
just to help you and give you extra credit. Oh, it's absurd. But that's how important we feel this is, right? I don't like giving out extra credits, right? I like people working for regular credit. But I'm willing to give it, that's how important I think it is to learn how to collaborate and work together.
No, but usually are they open on Saturday or?
I don't think so. Maybe, I don't know. That's a good question. I don't know the answer, but we could find out this Saturday because they're telling me they have to get me a key. So I think that's a no. All right, I know it's about time to go, but I thought I know you're really passionate about that, but I think it's important that we look at some old tests really quick. The reason why is I want to give you a feeling for what a test might look like so you can tell that I'm not making stuff up on you and you kind of have a vision of where to go. If you're really into the problem, keep working and don't listen to me, but we do need to be out of here for lab at 7, so just be aware of that. I'm going to look at last year's, spring 20. Oh my gosh, that was 2 years ago already? That's disturbing. All right, so take a look at this old test. Let's just go through it and look at the problems. Determine the units. Chapter 1. This looks like a nasty problem where you've got some sort of area you're trying to get, it's some kind of variation on mixed units, unit conversions, doing some math with these units and different notations. Notice that one's worth 6 points instead of this one, which is only worth 2 points. So we got to check the units, dealing with unit conversions and chapter 1 stuff. Here's a vector problem. We'll talk about this more. This happens to be a relative velocity. We'll discuss this in chapter 4, but essentially it's a vector addition problem, a tricky one. Here's a vector multiplication problem. Dot product, cross product, get the angle between. You got some vectors. Notice I included units, so you would have to remember, oh yeah, my final answer should have units. Here's a problem. Plug in some numbers. Can you plug in numbers correctly and not screw it up and get the correct sig figs? So this is the sig figs. Look at this, it's worth 4 points. Probably 1 point for the number, then the notation, then the sig figs, then the units. So it's really easy to lose points if you're not rock solid on chapter 1. Have you noticed that? Chapter 1 is important. You got to be good at it. This looks like the 29 and a fractions, right? Recognizing initial position or initial velocity or acceleration, moving left, speeding up, slowing down, etc., displacement, etc. Notice this is an XT graph. Here I did a VT graph. The same questions, just seeing if you could actually figure out the rules for a VT plot are different than the rules for an XT plot. Okay. This is chapter 4. We'll pick this up next time. Look at this. This looks like what we just did today, doesn't it? Max separation distance. Cop and the speeder. It's basically a cop and the speeder problem, except I called it P and Q. Whatever. There's this one, both of them have an acceleration. Oh my gosh. Oh man. So this is, yeah, those cop and the speeder, I'm going to make them gnarly. Don't worry. Here's an extra credit problem. Blah, 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 blah. Determine position as a function of time. You know this equation for velocity, separation of variables. It's all there. Let's go to the next one. All right, just walking you through. Okay, this is chapter 4, but we'll discuss that again. It's basically like integration, chapter 4. Here's one, do a unit conversion. Can you plug in numbers correctly without screwing it up and write it into chapter 1? Here's a graph. Can you get this stuff? And let's see, this happens to be an XT graph this time, right? This is chapter 4. I love this. Don't freak out. These problems can be tricky. Can you write down sig figs in notation? Can you do a cross product and get a hat vector? Can you get the angle between? Here's another vector addition problem. Here's a problem with 2 stages, right? 2 runners. So it's like a cop and a speeder problem. Extra credit. Oh, looks like separation of variables, doesn't it? One more or not? What the hell? I'm going to do it anyway. And then we'll get you out of here. If you got to go, you got to go. I understand. Can you plug in numbers correctly? Can you do notations, right? Can you figure out the units of some ugly equation? Can you do a conversion? Okay. Can you do math with a hole? Well, for an object that's got a hole cut out of it, and keep track of all the mixed units and unit conversions. Cop and a speeder problem, car 1 and car 2. 1D motion where you make a plot. All right. This looks like separation of variables. Do you see some patterns here? This is probably a chapter 4 problem. We'll do that next time. This is a vector addition problem. Ugh. Right, extra credit. So the extra credit, just so you know, it's really hard usually. All right, let's get you out of here. If you have questions, we can do it, but we got to get out of this room, right? Next class is coming in. I hope you agree we're getting some of these pieces, right? We're getting close. Chapter 4 is next. Oh my goodness. Yeah, do that homework so that when you go to do the practice test, you're not starting from scratch. Yep. And use the solutions. If that's what it takes to get through the homework, that's fine. Don't forget, you got practice tests, okay? Just try to gradually weed